Okay, Matt Roscoe here from the University of Montana, and a little video on our investigation of diagonals, quadrilaterals. So this is in particular, this is um, problem 6.4.1. Prove that a quadrilateral is a parallelogram if and only if the diagonals bisect each other. So a couple things. We're dealing with parallelograms, and it's an if and only if, so it's a biconditional. We're going to have to go prove it in both directions. And what we're really curious about is, does diagonal bisection, is it logically equivalent to being a parallelogram is really what we're proving here. So I'll go ahead and get started proving it in the forward direction. So I've got a little work done already. I've got a picture drawn. It's supposed to be a quadrilateral, a picture of a quadrilateral, I guess. So and I have the hypothesis written out. So just a few things maybe I could add to my drawing just to make it clear. Um, so the opposite sides are parallel. That's the definition of a parallelogram. So AD parallel to BC and DC parallel to AB. So how are we going to go about proving this? This is going to be rough, just a proof sketch. Wouldn't be a finished, I guess, product, but let's just talk about the ideas. I guess the first thing we're going to want to do is probably drawing the diagonals. Um, so I'll draw them in first, and picture like that, I guess. And we'll probably, oh, so draw in diagonals. What, DB and AC. I guess that since they cross, we're probably going to want to give this point a name. BCD, let's call it E. So I'll say call intersection E. And what we're trying to show, I guess, is that BE is equal to DE and that AE is equal to EC. It's fairly, it seems like the idea here would be to try to prove triangle congruence. So for example, if I could show that this triangle ABE is congruent to this triangle down here, let's see, ABE would be no wait, CDE. If I could show that those two triangles are congruent, then by corresponding parts of congruent triangles, I could show then that this side and this pair of sides and this pair of sides would be congruent. So at first glance, it seems like this is a tough order. The reason is that we don't have any sides of same length. So probably what we're going to have to do is identify a subgoal here to try to prove that some sides are of the same length. So how would we do that? Well, one way we could try to do this is we could think about trying to prove different triangles congruent. So I guess I'll grab my blue. So maybe if what I did is I tried instead to first show that this triangle was congruent, and I'm going to sort of draw it outside so that we can kind of see to that triangle. If those two triangles are congruent, then this side would be congruent to this side, and this side would be congruent to this side. So I think that's the first subgoal. And it's fairly easy to see how to do that since these are parallel. I guess this line would be a transversal for AB and CD. And if it's a transversal, then alternate interior angles are congruent. So that's what I'm going to go for first. I'm going to say that, and I can do that again. So if these guys are parallel, then alternate interior angles here and here are congruent. So we have two sets of alternate interior angles and a common share side. So by angle, side angle, we can get the two blue triangles congruent to one another. So that's what I'm going to go for. So let's see, alternate interior angles. Let's go first with, since BD is a transversal of parallel lines. Let's see, BD's transversal parallel lines A, B, and DE. We should probably we get what? Let's see, we get ABD congruent to angle CDB. Oh, sorry, CDB by alternate interior. And then I just do it again since BD. I got to be a little bit careful. So what I just proved was that this angle and this angle are congruent. So that's what I proved by 3, I guess. But I can't use the same argument to get this angle and this angle, of course, because they're not alternate interior angles on AB and DE, but they are alternate interior angles on AD and BC, so in this direction, I guess. Okay, so BD is a transversal on, I should say, of parallel lines. I'm just going to repeat the argument above. AD and BC, we get, let's see, so this will be angle ADB congruent to ADB, congruent to CBD. By alternate interior angles. And of course, BD is congruent to DB. By reflexivity. So what triangle? Let's call it BDA. Has to be congruent to triangle. Let's see. So BDA would be DBC by angle, side angle. By CPCTC. What do we get? We get DA is equal to BC, right? DA equal to BC. And let's see, CD, is that what I want? Yep. Let's see, but let's do it the same direction. DA, so AB. AB is congruent to CD. So now we have opposite sides congruent, which was, not given. We had to prove it because we have a parallelogram. Parallel sides is all we're given. But now we have opposite sides are congruent. And I think now we have enough to go after the pink triangles because we have a side opposite that is DC and AB, and we already have angles 3 marked as equal. What we need is we need angle, and maybe I should have done this too. These are the angles that we got by argument 4, I guess. So we have the angles marked 3 equal. Well, we could do this a couple different ways. We could either go after these two angles using alternate interior angles, or we could go after these two angles using what we would call vertical angles. If we go after these two angles, then our argument would be angle, angle, side. If we went after these two angles, then our argument would be angle, side, angle. Either one works. I'm going to go with the vertical angles. So I'll go here, 8 by vertical angles. I'll call it BEA. Is congruent to angle DEC. So I guess that's 8 right there. And we've got enough now to state that that the pink triangles are congruent. So I guess 9 by angle, angle, side, triangle, EA, let's see, EBA. So I went E to B to A, so I'll have to go E to D to C. And I guess the last thing is to get down to what we're trying to prove, that these diagonals bisect one another. So we should be able to make a statement now by CPCTC that this diagonal is bisected at point E and this diagonal is bisected at point E. So let's just see if that's the case. So let's see, at point E I have EB equal to ED. That makes sense, EB equal to ED. So I'll just say by CPCTC, EB congruent to ED. And let's see, EA congruent to EC. So EA congruent to EC, and that's what we wanted to show. So I got to be a little bit careful. That's, the forward direction. We know that this thing certainly works in a forward sense. I started with a parallelogram. I just drew in the diagonals, and through kind of a two-step process, I was able to get to a point where I know for certain that EA is equal to EC and ED is equal to EB. But remember that this is an if and only if proposition, so it's a biconditional. What we've shown basically is the forward direction. If parallelogram, then diagonals bisect. So, I mean, this really is just part 1. How would part 2 look? Let's try that. So this is part 2. We're going the other way, and what will be given is that two diagonals bisect, and what we want to show is that results in a parallelogram. So for this one I purposely didn't draw it because I thought it'd be kind of fun to just let the ruler guide us. So what I'm going to do is I'm going to draw in two diagonals of known length. So that one's 3 inches long, there's 1.5 inches. So that's where the diagonal is being bisected, right? So I'll do, say, another diagonal that's 4 inches long. So I'll put it in the middle, though, so that we're 4 inches long, and we get that sort of situation. So literally what I've done is I've drawn in two diagonals that bisect one another, and the question is, does that result in a parallelogram? Sure looks like it's going to. This is a great way, by the way, to use GeoGebra to test these conjectures. You know, build a parallelogram, investigate its diagonals, and then build diagonals, and according to the specifications, and see if it results in what we think it should. In this case, it sure seems like it's a parallelogram, but we haven't proved it. We don't know it for certain, so let's go ahead and try to prove this. Right away, what I notice is that we have sort of a side-side correspondence here and here and here and here. So if I drew a sort of, use my highlighter again here, it sure seems like this triangle and this triangle are going to be congruent. It's pretty easy to see the way that I could get these two angles congruent by vertical angles, and then I'd have a side angle side argument, which would give me then that all the angles would be equal. So for instance, this angle and that angle would be equal, and by the converse of the alternate interior angle theorem, that would be enough by alternate interior angles to prove that these two are parallel. So that's the route I'm going to go. I'm going to name this A, B, C, D, and E again. So I guess we should probably write down our hypothesis so we know what we're after. What should we say? Sort of BD and AC bisect one another at E in, and maybe I should put an if here, in quadrilateral ABCD, then quad ABCD is a parallelogram. So I period E AD is parallel to BC, and AB parallel to DC. So that's the hypothesis. Let's go ahead and get after it here. So how would the proof look? Let's see. I guess the first thing I would note is that the angles in the middle, or maybe we just say by construction. First, let's note the sides. What BE is congruent to ED, and AE is congruent to EC. Let's see. So number two, I'm gonna get after these two, this pair of angles right here. So let's see. By vertical angles, AED congruent to CEB. So what does that give us? That gives us two congruent triangles by what? Side angle side, triangle AED congruent to triangle CEB. By CPCTC angle, let's see, I want this one and this one to be the same, so I'll call this 4. these ones, just to mark, I guess, where the idea is coming from. ADE congruent to CBE, and then let's see, by alternate interior, we get that, let's see, since these are alternate interior angles on transversal, maybe I want to say something about that in the final proof, that viewing DB as a transversal of lines AD and BC, we can apply alternate interior angles, but hopefully you get the idea that we get that AD is parallel to BC. So we've got one set of parallel sides. We could march through the exact same argument using, I guess, the triangle unmarked on the top and the bottom here to prove that the other two pairs of sides are parallel, but I think probably it's pretty clear to the reader who's followed this enough. I would just say we can prove that AB is parallel to DC similarly. So I think that does it. Kind of a little bit less work on the converse than on, I guess, the forward direction. Here we get a simple side angle side argument that gives congruent triangles, and then an alternate interior angle argument that gives parallel sides. So I'll go ahead. I know that sometimes it's hard to read these watching on YouTube. I'll go ahead and make a PDF of these and upload them to the website so that you have the ability to take a look at those. And yeah, I hope that that gives you some sense of how to proceed. We're leaving, I guess, these three up to you. So prove that a quadrilateral is a rhombus if and only if its diagonals are perpendicular and bisect each other. And prove that a quadrilateral is a rectangle if and only if the diagonals are congruent and bisect each other. So kind of interesting to think about. If you can prove that a quadrilateral, a rhombus is a parallelogram, or a rectangle is a parallelogram, then you can use the results of 6.4.1. That is that the bisection comes along for the ride. But of course, you'll have to prove that they're parallelograms first. A rhombus, of course, is not defined as a parallelogram, and neither is a rectangle. A rhombus is just a quadrilateral whose four sides are congruent, and a rectangle is defined as a quadrilateral. Let me just think here. I had to look it up really quick just because I couldn't remember off the top of my head. If you go back, I guess, to page 9, that's where these are defined. So it's a rectangle is defined as a quadrilateral in which all four angles are right angles. So that's the definition. So if you need the definitions, they are on page 9. But anyway, so I hope that gives you a little bit of I guess this example. I hope that it gives you a little bit of sense of where you're heading in these problems in the book. And I'll look forward to talking them over with you once I get back. All right. Have a good week, everyone.